this section, we will cover immunoassays. In this section of the lecture, we'll discuss a few of the immunoassays that might pop up on the boards. The first one that we'll talk about is the precipitin reaction, or the Ochterlony diffusion assay. This is an older assay that has been used for a long time in the past to determine the presence of antigen or antibodies in the serum of a patient. Not likely to be found in a hospital in this day and age with the technology that we have, but still likes to pop up on the boards, so I want to make sure you're familiar with it. Basically what we have here is diffusion and precipitation. That's the whole idea. So if you look at the left, what we do is we take an antibody and we take an antigen, we set them into some media, and we let them diffuse towards each other. Once they come in contact with each other, they will form immune complexes and they will precipitate out. What you will see in the media is a line. So if you look here on the left, we have R antigen, for example. So we put R antigen in two places, and we put an anti-R antibody in a third place. As these antibodies and antigens diffuse toward each other, they're going to precipitate out, and what you see is a peak. The reason you see a peak here is that since R and R are the same, as they diffuse towards each other, remember back to your days of chemistry, that gradient will come to an equilibrium, and since they recognize that they're the same, they will stop migrating, and therefore you get this peak. Contrast that with the reaction of non-identity, where you have two different antigens, R and S. You put antibodies to both of them in a different spot, the diffusion will take place, and instead of getting a peak where the precipitation occurs, you get an X. Again, remember going back to your chemistry days, since R and S are different, they will diffuse independently of each other, and they'll keep migrating across until they establish an equilibrium. Because they'll keep migrating across, that precipitation line will continue to form, and therefore you get the X instead of the peak. Now in our third example, we have reaction of partial identity. In this case, you have R and you have this R1, which is a similar antigen, but not quite identical to that R. So if you use antibodies to R, the antibodies to R will recognize both of them, and so you get the peak point there, and then the R1, since it is a little bit different, it will continue to migrate across, whereas the R will kind of recognize it and stop. The R1, since it's different, will continue to equilibrate across, and so you get that partial non-identity. So it's kind of a combination of the previous two reactions. Again, take-home message here, you're looking for antigen-antibody complex formation. If you get a peak, that means you have two antigens that are the same. If you get a cross, two antigens that are different, and if you have a combination where you have half peak, half cross, that's partial identity. That's similar antigens. The agglutination assay is another common immunoassay. We use this when we're blood typing, right? When we're screening for blood type. So we have two ways we can do this, the slide test or the tube test. The slide test is up on top, so we'll talk about that one first. You take somebody's blood, you put it on a slide, and then you're going to take an antibody and see if it reacts. So let's say you have somebody's blood and you want to know if they have type A. You would take an anti-A antibody and put it on the slide. If that person has type A blood, then the antigen from the red blood cells and the antibody will form complexes, and it will cause clumping. And you can see that as the positive slide test. You see antigen-antibody formation, this complex formation, it will cause them to clump on the slide, and that's a positive test. That would mean that the person has type A blood. If the person has type B blood, for example, B antigen on the surface, and you put anti-A antibodies, there's going to be no interaction, no complex formation, no agglutination, so the blood will just stay spread out, and that would be negative on the slide test. Now the tube test, same idea, but we're going to do it in a test tube. So we put the blood in the test tube, we put the antibody in the test tube, and then we spin it down. If there's an interaction, for example, if you have type A blood and you add an anti-A antibody, then you have the complex formation. These complexes then will sterically spread out and coat the bottom of the test tube so that if you centrifuge the test tube, the blood won't pellet out. The blood will stay spread out because of the steric hindrance of the antigen-antibody complexes. That would be considered a positive test. So if you're looking down at the test tube like we see this circle, imagine looking down on that test tube, you're going to see the blood spread out along the bottom of the entire test tube because of that complex formation and the web formation. Now, if there's no interaction, if you have type B blood and you add anti-A antibodies, then there's no interaction. When you centrifuge it down, everything's just going to clump right at the very bottom of the test tube. So when you look at it, you look down, you see a pellet. That would be a negative. Flow cytometry is one of the newer types of immunoassays that we use, starting to come up on the USMLE boards. We need to understand what flow cytometry is. It's basically using immunofluorescence to be able to distinguish discrete populations of cells. So in this example, what we would do, for example, we're looking at, say, somebody's blood and we want to know how many CD4, how many CD8 T cells are in that blood. We would take antibodies to CD8s and antibodies to CD4s. We would put a red fluorescence marker on the antibodies to CD4 and a green fluorescence marker on the antibodies to CD8. We would then put them through this flow cytometer, and the flow cytometer would flash a laser light at each of the cells as it passes by, and would record, do they glow red, do they glow green, do they not glow at all. And then it would mark these on an XY type of plot. And so you could read out along this plot where your red glowing cells are, where your green glowing cells are. So in looking at this, it's broken down into quadrants. In quadrant A, those are high on the y-axis, or the red axis, and low on the x-axis, or the green axis. So these would be cells that were glowing red, but not glowing green. So you could deduce that these are cells that had that red glowing anti-CD4 antibody attached to them. So you would then conclude that those are your CD4 cells. So in that quadrant A, those would be your CD4 cells. High red, low green. In quadrant D, you have the opposite. You have high green and low red. So you would infer that those are the cells that were glowing green. Those are the cells that had the anti-CD8 green glowing antibody. So those are your CD8 population. Down in quadrant C, you have cells that are low red and low green. They're not glowing red or green. So what kind of cells would those be? Well, they wouldn't be CD4s and they wouldn't be CD8s. So those would be things like B cells, or those would be things like monocytes. We can use this technology to identify certain discrete populations of cells, and then we can characterize and classify a disease according to the cell types that they have. This concludes our discussion on immunoassays. In the next section, we will cover some case reviews.